welcome. Today, we are pulling back the curtain on energy and power. We're going to explore the invisible force that really is the engine behind just about everything that happens in our world. So let's start with a really basic question. What does a marathon runner, a car, or even your own brain have in common? Well, they all need fuel. They all run on energy. It's the essential ingredient for doing anything at all. So here's our game plan. We're going to look at how energy is a total shapeshifter. Then we'll uncover its one unbreakable rule. After that, we'll get into the speed of energy, which is power. And finally, we'll see how all this connects to, you guessed it, your electricity bill. All right, first up, let's talk about one of the coolest things about energy, its incredible ability to transform and change its form. You see, energy never really just sits still. I like to think of it as a master of disguise. It's always the same stuff underneath, but it's constantly swapping outfits, changing from one form to another depending on the situation. And these transformations, they are happening literally everywhere all the time. The spinning of a generator becomes electricity. That electricity flows into a heater and becomes warmth. Sunlight hits a leaf and gets stored as chemical energy. And hey, that sandwich you had for lunch, that's the chemical energy your muscles are now using to move. It's a non-stop cycle. Okay, so if energy is always changing its clothes, that brings up a really important question. Can you ever lose some of it? Or maybe create a little bit extra out of nowhere? And the answer to that is a huge universe-spanning no. This right here is one of the most fundamental rules of physics, the law of conservation of energy. It basically says you can't create energy out of thin air and you can't make it disappear. You can only change its form. The total amount you started with is always the amount you end up with. And a really fantastic way to see this in action is with something super simple, something we've all played with, a pendulum. Just picture it, right? At the absolute highest point of its swing, the pendulum just hangs there for a split second. In that tiny moment, it's not moving, so it has zero energy of motion, or kinetic energy. All of its energy is stored up, waiting. That's what we call potential energy. It's like a stretched rubber band, just ready to snap. And then, whoosh, as it swings downward, that stored potential energy gets converted into kinetic energy, the energy of motion. It gets faster and faster, and right at the very bottom of its swing, it's moving at its absolute fastest. That's where its kinetic energy is at a maximum, and its potential energy is at its minimum. Now check out this table. It shows the same idea, but for a falling object. As the height goes down, the potential energy drops. But look, the kinetic energy goes up by the exact same amount. And the most important part? That last column, the total energy. It stays at 800 joules the entire time. It's not lost, it just changes its name from potential to kinetic. Okay, so we've established that energy is what lets us do work. But what about how fast we do that work? Well, that's where our next topic comes in, power. So, simply put, power isn't about how much you do, it's about how quickly you do it. Think of it as a measure of intensity. The formula is super straightforward. It's just the amount of work you did divided by the time it took you to do it. We measure power in a unit called the watt, named after James Watt, a pioneer of the Industrial Revolution. And what it means is simple. 1 watt is equal to 1 joule of energy being used every single second. It's a direct measure of the flow of energy over time. This is a perfect example. Look, both girls weigh the same, and they both climb the same height. That means they did the exact same amount of work. But girl A is much more powerful. Why? Because she did the same work in less than half the time. Her power output is way higher, 160 watts compared to just 64. We can even run the numbers ourselves. Let's say a boy runs up a flight of stairs. First, we figure out the total work he did by multiplying his weight by the height he climbed. Then we just divide that number by the time it took him, which was 9 seconds, to find his power. And the result? 375 watts. That means for every second he was climbing those stairs, he was generating 375 joules of energy. Not bad. All right, let's bring all this theory back home. Literally. Let's talk about how this stuff shows up in a place you're probably very familiar with, your electricity bill. You see, a joule is a really, really tiny amount of energy. If our electricity bills were measured in joules, the numbers would be astronomical and meaningless. It'd be like measuring the distance to another city in millimeters. So for practical, everyday use, we need a much bigger unit.
And that unit is the kilowatt hour. You've probably seen kWh on your bill. So what is it? It's pretty straightforward. It's the total amount of energy a 1,000 watt or 1 kilowatt appliance uses if it's left running for 1 full hour.
And get this, that one single kilowatt hour, that one unit on your bill, is equal to a massive 3.6 million joules. It really shows you just how much energy our modern lives actually consume.
So why should you care about this? Well, because understanding the kilowatt hour basically lets you decode your electricity bill. It helps you look at your TV or your microwave, see its power rating in watts, and get a real feel for how much energy it's using and how much it's costing you. It's actually pretty empowering.
So, to wrap it all up, we've seen that energy is a master transformer, but it's always conserved, you can't make it or break it. We learned that power is just how fast you're using that energy, measured in watts. And finally, the kilowatt hour is the big practical unit we use to measure all that energy consumption in our daily lives. So, I'll leave you with one final thing to think about. From the sun's light becoming plant food, to that food becoming the energy that powers our own thoughts, every single aspect of life is built on energy changing its form. So, the big question is, could anything at all exist if energy didn't transform?